the second paper is regarding the impact of the floods on education outcomes. It is going to deliver evidence from the Bangladesh using the satellite and census data. It is quite typical, the big data, the analysis and the quantitative works on the developing evidence on this area.
So this is, thank you, Chair. This is a joint work with Mainul from BIDS and Paritosh from University of Dhaka. As you see, the theme of this conference is challenges and promise of human capital. And in this paper, we show that the natural disaster is a big challenge, a big threat to human capital accumulation. And we show that by combining satellite-based flood data and the census data of Bangladesh from 2011 to 2018. Little bit of motivation. As you know, there's ample evidence on the impact of natural disaster on physical capital, livelihoods, assets, and others. Because in most cases, these are the impact is direct and it is easily measurable. Right, but on the other hand, the impact of human capital, it receives the less attention, but for the same reason, because it is hard to measure, generally indirect, and it's a long-term impact. Though this literature is thin, this literature is growing, and most of the attention is on the health outcome. For example, Guterres, they found that the flood exposure in early life leads to stunting among children under 5 in Bangladesh. Caruso, they used Latin American data for 100 years, and they also found similar results. Early exposure to natural disaster has an impact on health and other human capital. But in case of education, the literature is thinner. For example, the Shah and Steinberg, they argued that the natural disaster can change the opportunity cost of schooling. That means it changed the rate of return of different investment. And they found evidence in support for that. For example, they found that when the rainfall is higher, children get out of school, drop out of school, and get into the productive work. So this is a very important JP paper that they wrote. And our paper contribute to this literature, and we argue that to the best of our knowledge, this is the first paper which examines the impact of flood on education outcome for Bangladesh. Again, a little bit of context. As you know, Bangladesh is a low-lying delta. Hundreds of rivers crisscross Bangladesh. To be exact, there are 700 rivers that flow over Bangladesh. It is located at the downstream of 3 big river basins, the Ganges, Brahmaputra, and Meghna River. The water from this river, compounded with heavy rainfall, cause floods in almost every year, and a devastating flood in every 5 to 8 years. And we argue that this it makes Bangladesh a good and ideal setup to study the impact of flood on human capital. Now I will show you 2 pictures. This picture is in Tangail district in 2017 flood. You see that the school is flooded and maybe some of the students are catching fish in front of it. And also you see the girls are having problem going to schools there because of logging water. And I think these 2 pictures nicely sum up the story that I'm going to tell in a few minutes. And to tell the story, I need some variables. So these are the education outcome variable. This comes from BANBASE, Bangladesh Bureau of Education, Information and Statistics. It's a government agency under Ministry of Education. They collect they collect high school data every year. That is, it is census in nature. And we consider 2 type of examination, public examination and school-based examination. Under public examination, we consider secondary school certificate, that is SSC, which the students sit for after grade 10, and junior school certificate after grade 8. And we consider 2 outcome variables. One is the passing rate and one is the percentage of students obtain GPA 5. That means we are considering the 2 tails of the result distribution. The school-based examination, we only consider the passing rate from 1 grade to the upper grade, and all the variables are available for boys and girls. So we have the gender breakdown. Regarding the flood measure, we construct the flood measure using NASA's MODIS satellite. It's a satellite that scans the Earth every day. And we use the algorithm of Sakamoto, which is widely used in economics literature, Guterres, Chen. This paper is published in AER. And we created the union level flood measure using the remote sensing data because we don't have the GPS of the schools, right? So, and our variable of interest is the percentage of area flooded in an union. The intuition behind this construction is that this MODIS raw data is processed to use some vegetation index, and using some pre-specified parameter values, this algorithm differentiates between water and non-water related pixel. And this water related pixel include permanent bodies, flood, and mixture. The mixture is land and water. And then we separate the flood from this other two components, that is permanent water body and mixture. And we use our three filters to exclude those things. One is the shapefile of the, we have the shapefile of the large permanent water bodies, so we can exclude these large permanent water bodies. We also treat the water related pixel in the dry season as permanent water bodies, so we exclude them. And also there are some water related pixel in the southern part of the country because of the swamp and the tide, and we also exclude them. So our flood measure is kind of a very conservative flood measure that we use. Using this flood measure, we construct this figure, the yearly variation of the extent of flood. You see that there is the takeaway message from this figure is that there's a wide variation across years of the extent of flood in terms of coverage. Since 2021 experienced the worst flood in terms of coverage, we use this year to illustrate how we construct the final yearly map. First, we construct a 16-day interval 23 maps of 2011. That means we construct this kind of 23 maps for all the years from 2011 to 2018. The red is the flood, blue is water, green is mixture, and ash is land. And you see that the red dot started to appear in the early June, then become prominent in the late June, peaked, I think it peaked in last week of July, and then faded away. So this is the monsoon region for Bangladesh. So using these 23 maps, we create one map. This is the yearly map of Bangladesh. So idea is that if a grid in a union, the grid is 250 meters square, union is found flooded at any point of the year in these 23 maps, we label them that this grid is flooded. For example, if a union has 100 grids and 20 grids are found flooded, then we call that the 20% of the union is flooded. That's how we construct the flood measure. Okay, empirical strategy. Our conceptual framework based on simple education production function following Todd and Wolpin, Hanushek, you all know about these papers. But the problem is we cannot distinguish between school level inputs and the household level inputs. So we have so you use the reduced form model. That means the impact of flood on education outcome direct. So we cannot say anything about the channels. The identification challenges, there are few identification challenges because we know that non-flood affected area, the schools in the non-flood affected area are generally better than the flood affected areas because they can attract better teachers, better students. So we cannot use the cross-sectional variation. That's why we use the within variation of the schools. So that's why we use the school fixed effect. And also in some years, the public examination can be harder than other years. And if that year coincides with the flood year, that means we erroneously picking up the effect of flood, right? So you also use the year fixed effect. Year fixed effect also take care of year specific changes, which is same for all the schools, like education change in education policy, exam policy, etc. We also rule out the spurious correlation over time between the exam results and the extent of flood. That's why we use the sub-district specific time trend. That means about 540 time trends for each sub-district. So this is the econometric specification you use for public examination. A is the outcome variable, the results in SSC and JSC. JSC, the junior school certificate. SSC is the secondary school certificate. Exam in school S in period T. There are two outcome measures. One is the passing rate, and another is the GPA 5. GPA 5 is the highest grade point average. Or FS is the flood measure. In year T of the union, the school S is located. Mu S and I forgot this, delta T. Mu S and delta T are the school and year fixed effect respectively, and nu ST is the sub-district specific time trends. And the similar specification for school-based exam, the only difference is that we use a different fixed effect. It is mu SG. This is the school grade level fixed effect. And this controls for school grade specific time variance in the school. So this is more restrictive model. Okay, here come the regression results. This result is for public examination SSC. The first three columns is for the passing rate, and the next three columns is for the GPA 5. Our variable of interest is the proportion of union flooded. We also control for the size of the school, because size of the school varies over time. That's the only time varying control that we could found from the census data. And you see that for the first three columns, the coefficients are highly significant at 1% level. It implies that 1% increase in flooded area in union results in about 3 to 6% drop in SSC exam, 3% drop in the passing rate of the SSC exam. Similarly, for GPA 5, the next three columns, when we control for school fixed effect, year fixed effect, and sub-district fixed effect, we don't find any significant impact. But we find significant impact when there is no year fixed effect here. That is the middle column here. Okay, let's move on to, oh no, shit, no. Yeah, this is the JSA exam. And also the first three columns is for the SSC result, and the last three columns is for the GPA 5. Our dependent variable is the passing rate of the JSA exam in the first three columns. Again, we find that the coefficient for the passing rate is highly significant for the first two columns. And when you control for year fixed effect, the significant level drops. And similarly, in the case of GPA 5, first two columns are highly significant, significance level drops when you control for year fixed effect. Now we'll discuss the gender dimension of our results, the floods, gender, and the public examination. And we do so by interacting the proportion of flooded area with female dummy. Again, first three column for passing rate, and second three column is for GPA 5, and this is for the SSC result. And you see that the interaction term is highly significant and very stable across the specification. That means girls' passing rate is about 2 percentage points lower than the boys due to floods. And when you look at the GPA 5, we see that the girls' share of obtaining GPA 5 is about 0.4% lower than the boys because of flood. This is a very striking result. And similarly, this result is for junior school certificate. The first three columns is for passing rate, second three columns is for GPA 5, and you see the interaction term. We find similar results. In this case also, the result is highly significant and very stable. And you see that about 2 percentage point lower of passing rate for the female compared to male due to flood. And in the case of GPA 5, it's about 0.15 or 0.1%. School-based examination, the passing rate is just, in this case, we separate the samples, and you see that for all students is a highly significant and negative. That means flood leads to lower passing rate. And this is more prominent in female students. And when we do the t-test and female students, it's highly significant. The difference is highly significant. So the takeaway message is that even in the school-based exams, students are affected by flood, their passing rate drops, and this drop is higher for the female students. this is for grade specific result. That means we are good at the impact of flood may vary with grades. And we find that this is true. And flood tends to impact the higher grades more than the lower grades. That is, in the grade 9 and 10, the grades, the impact are significant, and this significance is much higher, and the size of the coefficient is much higher for the female students than the male students. And we also check the severity of flood if there is any variation in outcome with the severity of flood. So we categorize flood into 4 quantiles, first, second, third, fourth. And the top quantile, we call it the severe flood. The third quantile, we call it the moderate flood. And the reference group is our first 1 and 2 quantile. And you see that it is the severe flood that matters, the severe flood that impacts the education outcome. When we show the results only for SSC exams here, but this is true for JSC and school-based exams too.
Kati, I'm sorry for making this interruption, but please finish presentation in 1 minute.
Oh yeah, I'm almost done. Okay, so we find that the floods do impact education outcome. It reduces the passing rate, JPA5, both in SSC and JSC exam. We have found significant impact in school-based exam. The impact of flood is more pronounced for higher grades, and it is the severe flood that matters. And more importantly, the female students are affected more than male students. And this is true for both public and school-based examination. I think I can conclude here. Thank you.